All right, welcome to session 1B on unconventional computing architectures. And we are going to start our session with an interesting talk on ReRAM-based Ising machines. Unfortunately, our speakers couldn't make it. Actually, none of the authors of this paper could make it to the conference due to visa issues. And we will have a recorded presentation followed by a live Zoom session. So please let us welcome our first virtual speaker, Rubing Song, who is a first-year PhD student from University of Rochester, supervised by Professor Tony Geng. He is interested in the intersection of machine learning AI systems and physics-enhanced machine learning. So please welcome our first speaker virtually. Thank you.
Use the energy of the system automatically. Finally, the learner of Rochester, advised by Professor Tony Geng. I feel sorry that I'm unable to talk with you excellent researchers in person due to visa issue, and thanks to the help from the committee, so I can make this record instead. Now, I'm really honored and excited to share with you our recent work, DSGL, which explores how to advance graph learning while harnessing nature's power within scalable dynamical systems. You may feel that the three keywords in this title sound unrelated to each other. However, this is just what we want to tell you today, that we can use dynamical systems to do reliable computing and significantly improve the graph learning. Due to the time limitation, we will focus on intuitively introduction and skip some details. Now, let's begin with the background. In recent years, the rapid development of machine learning has significantly increased the computing demands, which obviously exceeds the speed of Moore's law. In this post-Moore's law area, thanks to the efforts on digital optimization, like the new data formats, new architectures, and the Huang's law from NVIDIA, the gap is basically filled in the past years. And what we want to do is to find an orthogonal way to inject some new computing power in current computing systems. The community has been exploring new computing power for many years, and there are already many promising alternatives, such as quantum computing, photonic computing, and neuromorphic computing. As one of the explorers in this exciting area, our target is to find something with near-future promise, which is low power and low latency and high accuracy. And our solution is the dynamical system. From the evolution of stormy to a leaf fall to the earth, dynamical systems are existing everywhere in the real world. The interesting fact is that they are naturally performing complex computing all the time. For example, a drop of blue ink will spread in the water. If we think about this phenomenon in detail, it is a complex optimization problem about how to reduce the energy of this system. To solve this problem or to simulate this process with a digital computer can be extremely slow and energy-consuming. However, dynamical systems can naturally do it fast with almost no cost. It sounds perfect, but is this magical power even useful for computing? Maybe if we can use billions of micro robots to program or control the coupling intensity between the molecules in the water, then this water ink dynamical system may be able to help compute or predict something like this. Of course, this sounds too expensive or even infeasible. Is there any other way with which we can easily control this nature's power for computing? We need to program the dynamical systems, but how? The answer is, we can build an electronic dynamical system, which is very easy to control and program. Let's see an intuitive example for two customized coupled capacitors. Now we have C1 and C2 with some electrons, and if we connect them with different resistance, like R and R, to allow the electrons to move between them with different current, then let this toy dynamical system do natural annealing to the Nien energy state, and this is just the solution of the corresponding optimization problem defined by the customized resistance between the capacitors. In this way, we can easily build a seamless compatible dynamical system, and if we connect a lot of capacitors with programmable resistors, we can program a very complex optimization problem on it, and get the result by annealing in a speed of electron with nature's power. There are already existing works on Ising machine, a binary electronic dynamical system, which successfully solved some graph optimization tasks like the binary math card and achieved significant speed up. Then the question is, can we further extend it to more complex problems like AI, which raises scaling urgently and requires unlimited computing power? To maintain a realistic scope and due to the early stage of this research, we will focus on AI problems with graph data. In another word, only graph learning problems. Unfortunately, despite success in binary graph optimization, it cannot directly work for graph learning. There are many gaps need to be filled. There are three major challenges to extend the Ising machines to graph learning problems. First, the Ising model only supports binary values, while real-world applications are mostly real value. Second, how to learn parameters to construct the desired dynamical system and energy landscapes to ensure local minima match the results, so that natural annealing can solve learning problem. Third, this analog-based machine suffers a lot from its poor scalability. In this work, we will show how we solve these three challenges and build the first scalable dynamical systems for real-world graph learning problems. First, we propose a new model and corresponding hardware implementation to support the real-value computing. Then, we propose a learning method to map the graph learning problem to natural annealing of dynamical system. Finally, to improve the scalability of dynamical systems, we co-design a decomposing algorithm and a mesh-based network to perform co-annealing on both spatial and temporal dimensions. As a result, we achieve more than 10^3 speed up and 10^5 energy saving and higher accuracy over SOTA GNNs on A100 GPUs, showing the impressive potential of nature's power in dynamical systems. Next, I will introduce the technology details in 4 sections. In section 1, we will first show how to extend the original Ising machine to a real-value DS machine. We have proved that the binary Ising machine can never hold real value. Due to time limitation, we will skip the math and people who are interested can get more information in the paper. In summary, both the hardware architecture design and its corresponding energy function need to be improved to support real-valued annealing. Now let's see an intuitive explanation. For binary Ising machine, it requires all the currents in the coupling network to be zero at the stable point. And unfortunately, this system only has saddle points. With a little noise, it will never come back and can only stop at the boundary, like 1 or -1. To build a real-value support dynamical system, we add an extra resistor ring in our design as an energy regulator, which provides an extra stable condition for each node, allowing the currents in coupling network can be any value. These new systems have real local minima and easy to convert. We name it as DS machine. And let's see how we use DS machine to solve graph learning problem. First, the relationship between graph learning and dynamical systems. The nodes and edge parameters in graph can be represented by capacitors and resistors in electronic dynamical systems. The operator in GNNs is matrix multiplication, and the dynamical system performs a natural annealing process according to the coupling strengths between nodes to reduce the energy of the system automatically. Finally, the learning target of a dynamical system can be seen as to match the ground truth of training data to the local energy minima of the system. Training method rooted in various time-tested statistical methods, including the maximum likelihood estimation with neighborhood pursuit. And here we also skip the math and show the intuitive process. At high level, the training process adjusts the parameters of DS machine to construct its energy landscape with local minima matching the historical observations of the target problem. By so doing, the data distribution of the DS machine will align with that of the target problem. Then, during inference, begin with an initial state, get machines to natural annealing with electron speed to achieve the local minimum to get the predicted output. Now let's see how we further improve the scalability of the DS machine. The real-world graph data has a very important feature. Most of them has a community structure. Nodes can be highly clustered into different groups with dense intergroup connection and sparse intergroup connections. To leverage this opportunity, we do a hardware and software co-design to specify the coupling matrix into clusters of non-zeros and decompose the dynamical systems into many sub-DS machine systems, like the PE in the figure, and connect them with a sparse analog NOC, like the network of CU, and the detailed architecture of PE and CU are shown in the figure. The PEs can anneal together via the CU network, and we call it a spatial co-annealing process. This is efficient, that is poor analog without any AD conversion, and supports a short sensitive path to avoid physical limitation. However, it can only provide limited number of channels for inter-PE communication at the same time. What if the communication demand is over the capacity of the CU? To this end, we further improve our design to support temporal co-annealing. The limited physical channels developed by CUs will be reused by different pair of nodes over time through time division multiplexing. The equivalent can also be proved in math. This will slow down the annealing, but improve the accuracy while supporting more non-zero communications. Finally, let's see how powerful the dynamical systems are on that graph learning. For the accuracy, as shown in the table, our proposed DSGL outperforms all the SOTA GNNs on all the applications, even with the minimum latency, where only spatial co-annealing is used. The accuracy can be further improved with temporal co-annealing, and the more complex NOC can provide higher accuracy. For the hardware, DSGL outperforms all the SOTA GNN accelerators and A100 GPU by at least 10 to 3 times speed up and at least 10 to 5 times energy reduction. In conclusion, what we want to say is there is a new reliable computing source within huge near-future potential, the nature's power in dynamical systems, and it has a lot of potential to be explored in the future over graph learning. That's all. Thank you.
Thank you very much. So questions?
Hello, could you hear me?
Yeah, I can.
Hello, first of all, thank you for talking. And I wonder that what makes this work produce higher accuracy? Is it nature of Ising machine, or is there anything I missed from this talk?
Sorry, I can't hear you clearly.
What I wonder is that what makes this work produce higher accuracy comparing to SOTA of this work?
Oh, I get it. That's a very good question. Actually, in my opinion, the dynamical systems have an advantage over the graph neural networks. That is, for example, in GCN, the graph convolution neural networks, we may use 2 layers to propagation the information. But in dynamical system, you can imagine the coupling between the nodes is unlimited. Keep doing the propagation all the time, and it make if we use computing to represent it, it may contain like 1 million steps. So the information can be propagated more efficiently. That may cause the higher accuracy than the GNs.
So then you mean it is nature of Ising machine?
Yeah. that is nature power.
Thank you.
Yeah, you're welcome.
Okay, thank you very much, Huang, and let's move to our next talk then. Thank you.
Yeah, thank you, Professor.
So our next speaker is Cheng. He received his bachelor's degree in electronic engineering from the National Taiwan University in 2023. Now he's a master's student with the Graduate Institute of Electronics Engineering in National Taiwan University as well. His research interests include computer architecture, low power circuit design, and VLSI.
Again, laser, focus. Okay. Hello, everyone. I'm Zhang from National Taiwan University. Today, I'm going to talk about our work. ReAIM, a ReRAM-based Ising, adapted Ising machine for solving combinatorial optimization problem. This is a joint work of National Taiwan University, Chiang University, and Academia Sinica in Taiwan. Combinatorial optimization problem, abbreviated as COP, is a subclass of mathematical optimization problem, aiming to find a solution which minimizes the objective functions while satisfying the constraints. It is widely applied in many application domains. Most COP cannot be solved within polynomial time. Therefore, some heuristic algorithms are used to find approximate solutions. To efficiently finding approximate solutions for COP, a class of hardware solver called Ising machine has been developed. Given a COP, it can be formulated either as Ising form or Kubo form. The candidate solutions are represented as the quantum spin, and the Hamiltonians is represented as the objective function. The Ising solver algorithm is then applied to find the candidate solutions by flipping spins. Here we introduce the iterative process of Ising solver algorithm as simulating annealing. At each iteration, a candidate new spin is chosen by the flipping one or few spins, and the Hamiltonian difference between the new and original spin set is calculated. Then the local search algorithm, in our case, SA determines spin state based on the Hamiltonian difference. The SA accepts the candidate if the Hamiltonian difference is less than 0. Otherwise, if the probability with temporality will guide the decisions. By repeating this iteration many times, we can find the minimum Hamiltonians. Common Ising solver algorithm can be categorized based on the local search algorithm and the spin update mechanism. In addition to SA, like local search algorithm mentioned previously, other research also propose greedy-like approach, which only flip the spin with negative or minimum Hamiltonians. Moreover, at each iteration, single-flipped or multiple-flipped approach can be adopted to better trade-off between solution quality and speed. To efficiently solve COP, some hardware Ising machines have been developed. For example, DWF developed a quantum-based Ising machine. The main drawback is that it should be operated at a temperature near absolute 0. As an alternative, some quantum-inspired Ising machines propose to use CPUs and digital ASIC to solve COP. These quantum-inspired Ising machines, however, have separated computation and memory units, and running Ising solver algorithm which involves many matrix operations incurs a large amount of data movements. This energy overhead increasingly hurts the performance of this kind of Ising machine. Recently, several pin-based Ising machines has been proposed to implement parallel Hamiltonian calculation near the memory or directly in the memory. This design enables efficient computation and significantly reduce data movement. However, most of them only focus on limited scale problems and are customized for only a specific COP task. A customized Ising machine designed for a specific COP cannot satisfy diverse local search algorithm preference of different COP. For example, applying a assay-like local search algorithm and a multiple flip update mechanism can find a better solutions for a mascot problem. On the other hand, for the COP with more constraints such as traveling salesman problem, greedy-like approach, and single flip mechanism can be better. Considering the diverse algorithm preference of different COP, co-designing an adaptive Ising solver algorithm with configurable architecture is necessary. Therefore, we propose the first ReRAM-based adaptive Ising machine to efficiently find approximate solutions to various COP. RN offers high densities for storing large Ising or Kubo metrics, and its PIM architecture enables highly parallel Hamiltonian calculations directly in memory to minimize data movement. Through mapping Ising or Kubo metrics to RN crossbar array and converting spin vector into input voltage of the word line, we can get our desired result on the bit lines. Although the inherent resistant randomness of RN cell may lead to inaccurate computing result, especially when per cell current deviation accumulates. We can restrict the number of activated word line based on the error tolerance of the target COP to minimize its impact. To support various COP, we co-design an adaptive solver algorithm with a reconfigurable architecture. The adaptive solver algorithm selects hardware and solver parameters through static profiling and dynamic adaptation. Our reconfigurable architecture can not only support adaptive selection, but also enable highly parallel execution. We also designed methods to reduce the communication overhead for a large-scale COP. To support various COP, our adaptive solver algorithm follows 4 design guidelines. First, to reduce the capacity requirement, we statically select the formulation which requires fewer bits to represent matrix coefficient. Since our Ising machine is based on ReRAM, selecting the number of active word line requires careful consideration of the trade-off between solution quality and speed up. Our analysis shows us the best activated word lines are different between different COP, indicated that noise tolerance is different for different COP. So we use a profiling stage to statically select the activated word line. Third, the decisions of local search algorithm depends on both COP preference and the current spin state. Thus, we use a profiling stage to figure out the greedy or assay preference of the target COP and dynamically switch between greedy and assay based on current spin state. When the current spin state is far from the local minimum, greedy-like algorithm may be preferable to lower the Hamiltonians. In contrast, if current spin state is near local minimum, using assay-like algorithm can help escape the local minimum. Finally, since the optimal number of flips varies in different periods of annealing process, we need to dynamically select it in runtime. In summary, we select Kubo Ising form and run few iterations in profiling stage to select the activated word line and greedy assay preference. In execution stage, we will dynamically select the local search algorithm and the number of flip spins. Let me introduce a little bit more about the execution stage. It consists of trial phase and run phase. In trial phase, a set of candidate number of flip spins that is k are explored by duplicating Ising or Kubo matrix and concurrently run each class that with different number of spins for multiple iterations. The run phase then uses the k with the best result in the trial phase for the following iterations. These two phases run iteratively until we reach the stopping criterion. For each replica, we first compute the Hamiltonian difference and identify the spin which leads to negative difference. If n is large, meaning that there is still room for minimizing the Hamiltonians. our algorithm will adopt a greedy-like approach. Otherwise, if n is small, indicating current state may be trapped in the local minima, we will adapt SA-like approach. We also use a variable q to determine the threshold of n, and q is dynamically adapted according to the n in past few iteration, and also the greedy SA preference selected in the profiling stage. Next, we move on the hardware architecture of ReAIM. This is the overview of the architecture. There are 4 design goals. First, to support both Ising and cubophone, we implement several digital components in delta units of PE to perform the corresponding computation. Secondly, we also implement some modules in each tails to support the selection of greedy and SA-like approach. Besides, we enable parallel execution of ASA and parameter exploration. During the trial phase of the execution stage, multiple replicas should be run concurrently. If the tile numbers is sufficient, each replica can be run in parallel manner. If each replica needs multiple tiles number may be insufficient for all replicas to run concurrently. In this situation, since the matrix coefficient is shared by all replicas, we can leverage the intra-tile parallelism to run each replica in a pipeline manner. Finally, for large-scale COP, multiple tiles are required. Our target is to reduce the communication overhead for different tiles. In the following, we will explain each goal in details. For a large-scale COP, we adopt the divide and conquer method to separate the problem into several subproblems. We map each subproblem into adjacent tiles. Each subproblem can run independently in self-update phase for a few iterations. All subproblems exchange the change of the spin with each other only during the communication phase. This way, we can reduce the communication overhead. We use an in-house Python simulator to estimate the solution quality. For performance and energy efficiency analysis, we use design compiler to synthesize the digital parts and modify MNC to simulate our design at architectural level. Here we show the evaluation results on various COP. For all evaluated COP, our adaptive design can efficiently find high-quality solutions. Compared to COP, we can achieve comparable solutions with more than 100 times CBUP and only need 0.6% energy consumption. We also compare ReAIM with other Ising machines for mascot problem. Results show that our design achieved significantly shorter time to solution compared to CPU-based design or quantum-based or FPGA-based Ising machine. In addition, compared to the state-of-the-art pin-based Ising machine, we not only support SA-like local search algorithm, ReAIM achieved 2.2 times shorter time to solutions. In summary, we propose a RN-based adaptive Ising machine, which can dynamically select appropriate software and hardware parameter for target COP. We could design an adaptive solver algorithm with a reconfigurable architecture to efficiently find high-quality solutions. Our experience shows that ReAIM provides comparable solutions for diverse COP with superior performance, speedup, and energy efficiency over CPU-based baseline. In addition, RN also achieved 2.2 shorter TTS compared to the state-of-the-art ReRAM-based Ising machine. Thank you. This is my talk.
Any questions from the audience?
So you use 1 bit per cell in those debates. Can you comment on why you would choose 1 bit per cell as opposed to multiple bits per cell when one of the primary bands are?
Yes.
So you use 1 bit per cell in your paper. Can you comment on why you chose to use 1 bit per cell as opposed to multiple bits per cell when the primary advantage of RRAM density over SRAM would be the ability to use multiple bits per cell?
The most consideration is the randomness caused by the RN cell. If we use the multi-level cells, the noise will be too large and the computing result will be and will be hurt our performance and accuracy. So we choose to use a single level cells of ReRAM.
Thank you.
Any other questions? Okay, let's thank our speaker one more time. Thank you very much.
Thank you.
And our final speaker of the session is Cansu Demirkiran, a final year PhD student from Boston University. She works under the Integrated Circuits and Systems Research Group and is advised by Professor Ajay Joshi. Her research interests include integrated photonics and hardware accelerator design for deep neural networks. Welcome, Cansu.
This one. Perfect. Is the laser forward possible? Give me a second. Perfect.
So this one is
This
light?
one is.
Does it have a laser? Okay.
It's okay. If you want, you can try.
Alright, so can I? Okay,
Perfect.
good. Thank you. Hi everyone, my name is Cansu. I'm excited to share our work with you today, which was a collaboration between Light Matter and Boston University, and is about accelerating deep learning training using integrated photonics. As you all know, AI is ubiquitous. It offers very impressive capabilities, but these capabilities come with a very significant hardware cost. To reduce this cost and to sustain the growth of AI, there has been a renewed interest in photonics because of its capability of performing fast and efficient matrix multiplication operations.
This one.
Oh, thank you. Okay. Many prior works have leveraged this opportunity to build photonic tensor cores for deep learning hardware, but unfortunately most of these demonstrations have been limited to very small toy examples, and they target almost exclusively DNN inference but not DNN training. This is mainly because it is quite challenging to achieve high precision and high dynamic range using photonic computation. Okay, sorry. Oops. In photonic tensor cores, these matrix multiplication operations are performed in the analog domain, and the data are represented as fixed point numbers. The precision of these fixed point operations depend on two things. First is a ratio between the optical signal and the analog noise present in the photonic hardware. And the second is the precision of the data converters, DACs and ADCs. These data converters are necessary to switch the data between the analog and digital domains before and after every matrix multiplication operation. The precision of the ADCs at the output is particularly important because we typically start with low precision data, and as we perform multiply-add operations, the bit width grows, and the outputs require a higher bit precision to capture the information fully. So depending on the precision of the ADCs, we might lose some information here, which might cause accuracy degradation in the DNN. This creates a trade-off between precision and energy efficiency in systems like this. We practically have two options. The first option is to use high-precision ADCs, which is advantageous in terms of eliminating the information loss. But if we look at the energy efficiency, as you can see from the graph as well, there is a nonlinear and exponential relationship between the bit precision and the energy consumption of ADCs. So this causes an impractically high energy consumption in high precision ADCs. The second option is to use low precision ADCs. This is a more energy efficient design, which is the common practice today. But this design causes an information loss on every dot product performed in the analog domain and on every partial output, and this information loss accumulates and causes accuracy degradation in DNS, especially as we use larger vector sizes. So both ends of this trade-off are not very desirable. To locate ourselves at a better place in this trade-off, we propose to use an alternative numeral system, which is a residue number system, or RNS. RNS is based on modular integer arithmetic. It allows us to break high precision operations into multiple low precision operations, which are independent from one another and can be performed in parallel. So on the right, there is an example. In RNS, we use a set of coprime integers, which we call moduli. Here, they're represented as M1, M2, and M3. And we represent each integer, let's say A and B are integers here. We represent each integer as a set of smaller integers, which we call residues. To obtain residues, we perform modulo operations on the initial integers A and B with each modulus in the moduli set. So we do A modulo M1, A modulo M2, and A modulo M3. Same for the integer B, and we end up with 3 residues per integer if we're using a set with 3 moduli. If we want to perform a multiplication, for example, between these 2 integers in the RNS space, what we do is we perform separate multiplications between residues. So we multiply A1 with B1, A2 with B2, and A3 with B3. So instead of performing one big multiplication, we perform 3 smaller independent multiplications that can be performed in parallel. So these multiplications are not regular multiplications, but they're modular multiplications. And this guarantees that the output residues will have the same range of values as the input residues, so that the bit width does not grow during operations. And after obtaining the output residues, we can uniquely reconstruct a single integer value and switch back to the binary number system. In addition, RNS is closed under multiplication addition, so instead of just one multiplication, we can also perform matrix vector multiplications or a full matrix multiplication operation. So we use this approach to perform matrix vector multiplication operations in the forward and backward passes in deep learning training. So this is the full data flow of our training accelerator, Mirage. And this data flow is shown for the forward pass. So we start with an input matrix and a weight matrix, which are stored in FP32 and typically are larger than the photonic core sizes. So we first tile them into smaller pieces. And then we pass these tiles to the block floating point format, which is advantageous because block floating point or BFP format assigns a shared exponent for a group of values, and the mantissa bits of these values can be used to perform integer arithmetic. At the same time, because there is an exponent value, this data format can also provide a relatively high dynamic range, which is quite important for deep learning training. So by using the mantissa bits of these BFP data, we can pass these signed integers into the RNS space, and we can perform RNS operations, matrix vector multiplications in the RNS space. Because we perform one matrix vector multiplication per modulus, we will have multiple photonic modular MVM units. And because these multiplications are, again, modular, the range of values will be the same at the input and at the output, so we can use the same precision for DACs and ADCs without any information loss. Then the upper residues can be converted back to the binary number system, and then can be fed to the next layer of the network. So one of the major changes in this data flow is modular arithmetic with silicon photonics. So here on the left, you see a Mach-Zehnder interferometer, which is a very commonly used device for modulation in photonics. So this device has 2 arms and 2 phase shifters, and once an input signal passes through this device, the device applies a phase shift on the input signal. So this phase shift is proportional to the applied voltage to this device and the length of this phase shifter. Because the length is fixed once the device is fabricated, the common approach is to change the applied voltage so that we can change the amount of phase shift introduced to the signal. But for our purposes, we wanted to use both of these values, both V and L, to modulate the phase shift and perform the multiplication in the optical phase, which will be helpful for the modular operation, but I'll get there in a second. So to use both values to be able to change the length, we split one phase shifter into multiple digits. Each digit has a length proportional to the weight of the binary digit, which goes as powers of 2. So the length goes as 1, 2, 4, 8, and so on. So this figure shows a 3-bit example. For example, if I want to multiply 2 operands x and w, I can use one of these operands, x in this case, to turn on or off these digits. And effectively, I can change the total length of the active part of this phase shifter. So if the digit is 0, I can turn off this phase shifter completely. If the digit is 1, I can turn the phase shifter on. And if it's off, I can turn the least significant bit off. And the second operand can be encoded as an analog voltage value, which is similar to the traditional approaches and can be applied to all digits of the multiplier. So in a setup like this, the phase shift that we obtain at the end of this device will be proportional to x times w. But once we capture this phase, the phase shift that we observed will also be modular with 2 pi because the optical phase is modular with 2 pi. And by introducing a scale factor, we can also perform modular operations with arbitrary integers, but not only 2 pi. And a design like this enables us to perform both multiplication and modular operation in the same device. By cascading multiple of these multipliers, we can build modular dot product units, and by using multiple rows of these units, we can build modular MEM units. And because we are performing RNS operations, we will need multiple of these units to match the same throughput as a non-RNS-based approach. To build a full accelerator, we used multiple of these sets of MEM units. We built forward and reverse conversion circuits to switch between RNS and BNS. We built conversion circuits to switch between FP and BFP. We used multiple SRAMs to store different types of data. And then we used this accelerator to train networks. On the left, you see accuracy results. As you can see, our accelerator can achieve the same accuracy as FP32 with RNS-based 5-bit arithmetic, 5-bit integer arithmetic. And the Mach operations are 20 times faster and 60 times more energy efficient than FP32. But we also looked at different data formats that are more efficient than FP32. We looked at different workloads. We looked at ISO energy and ISO area scenarios. We used systolic arrays to implement these other data formats. And our results show that our accelerator can achieve approximately 24 times faster training and 32 times lower EDP in an ISO energy scenario, and it consumes approximately 43 times lower power in an ISO area scenario. To conclude, we proposed an RNS-based framework to train deep learning algorithms, and we designed an RNS-based photonic accelerator, and we showed that we can achieve the same accuracy as FP32 training. Our accelerator, Mirage, compared to the most efficient data format available in digital hardware, it can achieve approximately 24 times faster training and 32 times lower EDP. That finalizes my talk. I'm happy to answer any questions you may have. Thank you.
Okay. It's a great talk. Quick question. So you see a lot of benefit in the matrix multiplies. What's the conversion cost of the moving data from the logic domain to the optical domain? And how does that compare to the actual calculation cost?
It's a good question. So these numbers actually account for all those costs. So we included the matrix multiplication cost, which is very efficient compared to digital solutions. But it is a very important point because we need to switch between digital and analog domains, and we need to switch between optical and electrical domains. So one advantage of this design is that because we use one operand as we use it digit by digit, it is a digital value, so we don't have to pass this operand into the analog domain or into the optical domain. But we have to only switch one operand into the optical domain. So I can't recall the exact percentage, but I would say this design is dominated by the laser power, the matrix multiplication, the power consumption of matrix multiplication operations. And the reason being is that we reduce the bit precision of these ADCs and DACs and optical to electrical circuits. And this reduces the overall percentage of those units in the design, if that answers your question.
Got it. Thank you.
Great talk. I have a question regarding the area. So can you comment on the size scalability for this device?
It's also a great question. So in this device, because we split the phase shifters into multiple shifters, this design is not the most area efficient design. And as we increase the total length, this comes with a higher optical loss, and this comes with a larger area. So in terms of scalability, this design is definitely limited by the area of the total chip, and it is limited by the optical loss. And we performed a design space exploration, and we found a sweet spot that we can achieve these numbers and these gains.
Thank you.
Thank you.
So, thanks everyone. This concludes our session. We will continue with the best paper session at 11:15 on the opposite side. Thank you.